Hi everyone. So 27.2 is going to build on what you did in 27.1, where you were drawing some electronic configurations for some atoms. We don't need to worry about the S, P, and D stuff for the time being, but we're interested in trends for this. So we're going to be picking up some Unit 1 things. Here's a periodic table. It'd be useful to have one of these in front of you when you do this topic. We're going to see what happens on this periodic table as we go across and as we go down. So what are the trends across those periods? To do that, we're going to need to know a few new terms. So one of them is atomic radius. This is a rather bad drawing of an atom here. Imagine this ring here, because we're going to see the 1 is the outer shell of the atom, and where I've got this number, that is the nucleus. So imagine we've got those things going on. That means that the radius is the distance from the center, where the nucleus is, to the outside. Okay, that distance I'm going over with my cursor there. Easy enough so far. The other thing we're going to go for, or we're going to learn, is ionization energy. So this is another, possibly a new term. This time I'm thinking about the electrons on that shell. I've still got a nucleus in the middle, and the ionization energy is the energy required to basically do this, to move one of the electrons off. As you know, ions are things with a different number of electrons to what they'd normally have, and when we're thinking of ionization energy, we're thinking of removing it to make a positive ion. Okay, removing one of those outer electrons. Last thing to know before we move on is shielding. Those two concepts come about because electrons are attracted to the nucleus in an atom, as you know, because the nucleus is positive, these are negative. So there's an attraction towards that, and let's say I've got an electron here which wants to be attracted to the nucleus at the center of an atom. Well, it would be attracted to that one, so it would go towards it, it would join the atom. Now over here, on the right, this electron is still attracted to that nucleus. There's a positive nucleus there, and there's a force of attraction. However, we already have 2 electrons on the inner shells of this one getting in the way. So that electron is sort of, you can think of it as, well, it's negatively charged, isn't it? So the electrons on here are negatively charged. This electron's negatively charged. So this region doesn't seem so positive anymore. There's less of an attraction for this electron towards that. Okay, so the presence of these electrons between this electron and the nucleus reduce the attraction compared to if it wanted to be attracted just over here. So that's shielding for you. Now the impact of shielding is if I've got these 8 electrons on the outside, I haven't drawn my charge in here, but there's nucleus there. These 8 electrons are less attracted than you might expect them to be towards that nucleus because of these inner shells of electrons. So if they're less attracted, they're going to be a little bit further away. Okay, so that's what we get from less attraction. Okay, so let's start talking about the trends you need to know. Now we know what atomic radius is, we need to know how it varies when we look at the periodic table. Well, the greater the charge on the nucleus, the greater the attraction of this outer shell towards it. Okay, so if that is and the more attracted it is, the closer the electrons are pulled. Okay, as there's a more positive charge bringing them towards it. So that's how far they are if the nucleus has a 2+ charge. If the nucleus has a 3+ charge, they're going to get more attracted. Okay, they're going to get sort of sucked towards that. So if the charge on the nucleus is increasing, we expect the outer shells of electrons are going to be more attracted. Let's look at this in a bit more detail. Here you can see I've got an increasing charge of my nucleus. I've got a bit of the periodic table here. We're going to look at boron through to carbon through to nitrogen. We're going to look at the trend here. Well, I've shown all the electrons this time, and as you can imagine, the thing that I've just shown you, the simpler diagram, is going to apply here as well. These are going to get smaller as they go. However, you also need to consider what's going on between the outer shell and the inner shell, sorry, and the nucleus. And the thing that's between the outer shell and nucleus is this inner shell, which we've decided is going to shield the outer electrons. Now, this is important. Each of these inner shells in these three atoms is the same. So the shielding effect they're going to have on the nucleus is the same. So the only thing changing from the point of view of these shells on the outer, sorry, these electrons on the outer shell, from their point of view, the shielding is the same in each of these atoms, boron, carbon, and nitrogen. So that means the only thing that's changing is that charge. So if that one's sitting like that, then when we increase the charge in the nucleus, we must be ending up with something that's closer. It's drawn in like that. Increase it again. Much, much closer. Probably going to get this wrong, but you get the idea. Drawn really close, like that. Okay. The electrons don't get small, of course. That's just a limitation with the method I'm showing you. Okay, so that's one trend we need to know. As we go across, because the shielding has stayed the same, but the charge on the nucleus has increased, the atomic radius has decreased. So even though there's way more bits and bobs in this atom, way more protons, way more electrons than over here, this is actually the smaller one. Okay, this is the smaller atom. Okay, next thing to look at, let's go down. So we're going to look at lithium and sodium. You can find those on your periodic table now. Well, let's have a look at lithium. It's got 3 shells, and in sodium, sorry, 2 shells and 3 shells in sodium. That nucleus is not in the middle, is it? So that one we do need to count. We do need to count how many shells are there, because the more shells, the bigger the atom. That's more straightforward. Okay, so that one we would need to count. More shells means bigger atom. The other thing though is these outer shells, of course, are shielded. There's some shielding between this outer electron and the nucleus, so we can maybe draw that a little. Oops, we can maybe draw it a little bigger than I've drawn it so far, if PowerPoint will let me do so. So that it's not quite going to work now. That's a little bigger than what we've drawn initially. Okay. This one though is going to be even more shielded. So this outer shell here is shielded by these 2 shells over here. So if I just put that one back so I've got more space. So there's some shielding of the inner one. So the inner one is going to be a little further out than we expected. But crucially, because of all that shielding, this one's going to be, oops, this one's going to be loads further out than expected. This one and its electron are going to be loads further out because of all that shielding. Not very attracted to that nucleus at all. Okay, so that's some trends in atomic radius. Trends in ionization energy now. So here we have our 3 atoms again, and we want to know how easy is it to pull an electron off that. How easy is it to do that? Well, you might be able to see why I've used the same image here, because that's going to depend on how attracted each electron is to its nucleus. And how attracted each electron is to its nucleus depends on how big the charge in the middle is and how much shielding there is. So the pattern we're going to see is exactly the same. It's very easy to remove that electron. because there's only a 5+ charge. Very hard to remove that electron because there's a 7+ charge. And just like last time, the shielding is the same. So the change in shielding will make no difference there because there is no change in shielding. However, there is a change in shielding going down a group. Remember, I should have said this earlier. Down is the groups, across is the periods. Think back to assignment 1.1. So this one, not much shielding, very small atom, very close to that 3+ charge. That's going to be quite hard to remove because of how close that is and how little shielding there is. So this one, you might be tempted to think, well, that's an 11+ charge. That was only a 3+. This one must be much harder to remove the electron. Well, no, because of the shielding and the distance, you can see here, this, oops, it's not working particularly well. This is very easy to remove. Well, you get the idea. So that one is quite easy. So let's just add that. Bear with me, I'm going to add that onto there. There it is. Okay, so those are our trends. Your job is going to be to do a little summary. So you should be able to see this in your theory booklet, and I'd like you to be annotating it now. As we go across like this, what happens to those radii? Well, they get smaller, and you can tell me why. Why do they get smaller? You can write that there. As we go down, again, what happens and why? I want a little like mini paragraph for both. And you're going to repeat yourself in a minute. I'll come back to that in a moment. So key things, how many electron shells are there? So is the shielding staying the same or is it changing? And therefore, how far away is it going to be? What happens to the radius? Beneath that, you've got this drawing, which is showing basically the same thing, but we can use this to summarize the ionization energies. It gets harder to remove an electron as we go that way. It's easier to remove an electron as we go that way. Why? Same set of reasons. Number of electron shells, shielding, and that distance makes it easier to remove. So when you do this assignment and when you do these next activities, you're going to write a lot of the same explanations for different concepts. Okay, we are expecting to see the full explanation, even if you've written it once already on your worksheet, you'll just write it again. That brings me on to the worksheet. So jobs today will include doing just that, what I've just asked you to do. So annotating this page and some of these tasks. Okay, so this time, this is a first ionization energy one. This time we haven't said it's increasing, we've actually given you the values. And for the pass, for this assignment, you will describe what's going on in one sentence. It's increasing, basically. To get the merit, you're going to explain why. Same for this task, and same for these two. One little note, you'll notice that the numbering is a bit odd here. That is deliberate because this numbering will mirror the numbering we give you in the actual assignment. So you know which bits of your theory are going to help you with which. Okay, thanks for watching.